back to the combo classroom for a little other nighttime stream like I enjoy doing sometimes. It may be actually the last long live stream for a little bit, just because I have some plans for some bonus videos and other sorts of bonus content that I'll want to be getting back to. I used to put out bonus videos that were sort of between a short or main episode, which are a little more condensed, and a live stream on this channel. And I want to get back to that. Some things that are live streamish, but a bit more condensed into just singular video releases. But today, or tonight, it is a good time to chat about some strange proof techniques. This is somewhat a follow-up to the last combo class episode that I released. And let me pull things open while I'm discussing this. And the last episode I put out on my actually main combo class channel was about irrationality proofs, meaning proofs that certain numbers are irrational. And while that's not necessary to have seen before you watch this stream, it is linked in the description if you want to watch it later. And today, this is somewhat a follow-up to that, just because I wanted to discuss some other general types of proof techniques. You see, in that episode, we were using proofs by contradiction. And proofs by contradiction are just one of many types. And we'll see other sorts of things in future episodes and different sorts of content of mine that will make sense to include proofs within. So tonight, I thought, why don't we look over a general sense of some different types of proofs that one could do. A proof by contradiction, like we talked about in that episode, is when you assume that the opposite of what you're trying to prove was potentially true, and then go down that train of logic to prove that that would lead to a contradiction that made it impossible for that to have been the true statement, and so its negation, the statement you were trying to prove, ends up being proven. For example, to prove certain numbers are irrational, it can be easiest to try to prove that, oh, what if they were rational? What if they could be expressed as a fraction, and prove that that leads to some contradiction? And here, why don't we take a peek at what Wikipedia says to begin are some different sorts of other proof techniques you might see. And then after we look at some of the more actual logical ways that are useful to prove things, we'll also look at some jokes of different sorts of names of proof techniques that some people may try to use when they are, essentially committing the pseudoscience of math. Things like good old Terence Howard's 1 × 1 = 3 proofs, and other people who maybe think that they've already proven the Riemann hypothesis or Collat's conjecture in a couple pages. These may be showing examples of some of the more jokingly named proof techniques that are not actually proving anything. But first, things that can prove things. We have direct proofs, and a direct proof could just be that within your definitions, it's easy to combine your definitions in a way that leads to the result being clearly true. And here they have an example that adding 2 even numbers is always even. Since that's the one they have here, why don't I create a slightly different version, which will be, let's say we want to prove that 2 odd numbers is always even. Because 2 evens goes even, 2 odds goes even with addition, and it takes an even and an odd to go odd. Now, if we were adding 2 odd integers, they could be written as 2a + 1 and 2b + 1 for some integers a and b. The sum of those is 2 times a + b + 1, all in parentheses, because we had a 1 there and a 1 there, which adds to 2. So everything has a factor of 2. we would have 2 times a plus b plus 1 in the parentheses. And similarly, that is twice something that must also be an integer. And so it's even. So this is just using definitions to come to some conclusion. Now, here is an interesting one. Induction. I don't think I've used this yet when proving anything on this channel, as far as I can remember. But it is a common proof technique that is used in many cases. What it essentially is proving that if each n for something holds, then n plus 1 holds, and then just needing to prove it for a very small case, typically 1, and then all the numbers past that follow. So, for example, if you add some proof of primes, I'm not sure if there is this type of proof of the infinitude of primes. There probably is of some form. But if you had a proof that for each prime number, there's another after it, you'd only just have to prove there is 2 as a prime number, and then you'd have an infinite amount of them proven. Now, really, the proof of the infinitude of prime numbers that's simplest is more of a proof by contradiction, but there are other pretty simple proofs of that as well. In fact, one of the first episodes I made on my combo class channel ever was about proving things about primes. Now, here, past induction, which is a quite interesting one. Well, let's see an example here. They say that all positive integers of this form are odd. This is funny because this is sort of related to the assumption they used in this proof. Now they're, I guess, down here trying to prove that. Like a definition of what evens and odds can be expressed as. We could say 2n plus 1 or minus 1 in terms of this just being any integer, and either of those result in an odd number. So here we say for n equals 1, let's just test it. Yep, it's odd. Okay, so for number 1, it's true. Now we prove that if this is odd for any n, that it plus 2 must also be odd, because this is an assumption. You know, proofs are funny because you have to choose which assumptions you are going off that you assume to be common knowledge, or assume that you don't have to include the proof of that in your proof. These aren't formal proofs, but they're just examples. But they're using the assumption that adding 2 to an odd number is another odd number. So we have now showed that for any n, if one of them is odd, it plus 2 is odd. Well, now we can quickly arrange some things algebraically to show that this is always odd. Now, here, we have a proof, not quite contradiction yet. This is the one I was discussing, proof by contradiction down there. We first have a proof by contraposition. And that is basically taking, in terms of logic language, you would say this is called P implies Q. And it's often written with like P and then an arrow thing and then Q. We're going to do logic episodes at some point. And in logic, what this means, because it needs a clear definition, it's not the same as language, where sometimes you might say, like, if I win the lottery, then I'm rich, and we know that is one type of thing, then, or let's say if this was false, as an easier example, if it's not true that some P implied some Q, in language, you might not consider it to be like the statement that if Santa Claus exists, then, okay, we'll go into logic episodes later, but I'll just say, because this is just a small singular proof. What this means is it's not the case that P is true and Q is false. That's basically all it means. And so in language, there's a lot of other ways you could assume this means something, like that P directly led to Q. But here it doesn't mean P had to have caused Q in some way. It just means it's not the case that P is true and Q is false. What's weird about that to some people is that in logic here, we have to assume that means that if P is false, this statement is true regardless of Q's status. That, like, if we say, if -2 is odd, then 50 is more than 100. That might seem absurd. You're like, that doesn't lead to the other, and 50 is not more than 100 for sure. But we could say logically it's true because it's not the case that -2 is odd and the other one's false. So this is saying that the opposite of that is that if not Q, then not P is the opposite of this. And so sometimes you can use that to establish a proof. Their example here is, suppose X is not even, then X is odd. And what we're trying to prove here is that if X squared is even, so is X. The product of two odd numbers is odd. Hence, X squared equals X times X is odd. Thus, X squared is not even. Thus, if X squared is even, the supposition must be false, so X has to be even. Now, this seems like a kind of silly proof. A lot of the steps you're like, well, obviously. But sometimes, you could have a more complicated proof that also wanted to use the contraposition. Now, here we have a proof by construction. A proof by construction is if you're wondering if a type of thing exists and you demonstrate one. So let's say, as a really oversimplified example, let's say if you were like a caveman and didn't know much about math, and you were like, whoa, you can have triangles and squares and pentagons, these have more sides. Could you have a shape with 100 sides? Well, someone could draw a shape with 100 sides, and that would sort of be a proof by construction. Now, here we can say a good example will come up when we go into transcendental numbers more, because this guy Liouville, the Liouville numbers are a certain type of transcendental numbers, and basically he showed one of them existed by making one. He made a type of number with a formula that he showed was transcendental, instead of, that was before we had proven numbers like pi or e were. Now, it can also, as they note here, can be used to construct a counterexample to disprove a proposition that all elements have a certain property. So if you were like, well, I wonder if all primes are odd. Well, just by pointing to the number 2, you've kind of, done a proof by construction of that weird form. So, what about a proof by exhaustion? Well, we talked about the 4-color theorem once, and I mentioned this was one of the times where computers helped mathematicians, and this was when mathematicians were able to prove that you could color any map with 4 different colors, any 2D planar graph type map, similar to the type you're used to, with 4 colors, so that no matter how you draw the barriers of your fictional map, that no 2 neighboring regions are the same color. Which at first you'd probably assume, if you just were, throwing this question out of the blue, that it could take up to an arbitrarily large amount of colors, depending how you draw it. But it only takes 4. And they had proven 5 or less, but to prove 4, they narrowed it down to, with mathematicians doing this portion of the work, this amount of cases, but they're really big cases. And so a computer program checked a bunch of them. Like I mentioned, it was kind of controversial because how much do we trust that? And that's actually a good time to go to one other article I have pulled up, which is noting a non-surveyable proof. that is an interesting term that I just came across recently, that, this is a term I would have used before if I had been familiar with it, because I've mentioned this concept. Proof that we have to wonder to what degree we're trusting something like a computer because it's too long for a human to verify. And to some degree, really long proofs, like list of long mathematical proofs, including the classic classification of finite simple groups over 10,000 pages. They're still trying to simplify this and having trouble doing it. Now, a lot of these other ones we can see hundreds of pages long for many classic proofs. And when computers have to help with certain things, here's notes on that. Long computer calculations. Verification that checkers is a draw, we needed help with a computer from. Calculations of the biggest digits of pi we know, we needed help. Showing a Rubik's Cube can always be solved in 20 or less moves. Showing a Sudoku needs at least 17 clues. These are all things we needed a computer's help from. Now, here we can note that, it's an interesting philosophical thought to what degree we trust computers versus robots. And some proofs we almost could apply this semi-non-surveyable type to, just including really long proofs that only a handful of mathematicians have read all of. There's got to be a small handful of mathematicians who have read all this and understand it on the level that the mix of authors on it intended. And so it's very hard to double check it, How many people are double checking this thing each year? So to what degree do we need 20 humans to check it, or 30 humans and 12 computers, or, it's a arbitrary cutoff that raises questions of what we trust in a proof. But generally you do often get the sense, with these ones they're more questionable, but you often get the sense with some simpler proofs that some of them are so beautiful that you end up not finding any flaw in them and can even reprove them many different ways. So that's even the ideal if you have a problem, to try and prove it in multiple of these ways. Now we have a probabilistic proof, which is, this is using probability, and it's sort of like a proof by construction, but it's a sort of vague term here, but it seems to me like it refers to when it's not quite a proof. That, although here they're noting that a probabilistic proof shouldn't be confused with a plausibility argument. So let's see. They're saying that one seeks an object with a property from a large set of candidates. You assign a property for each candidate, and then prove there's a non-zero probability a chosen candidate will have the property. And it doesn't say which candidates have it, but the probability could not be positive without at least one. So that does prove something, for sure. It doesn't always prove the full case of what you wanted, but it proves a step in the right direction. I don't know if this is what they used for this, but it reminds me of how we don't know whether e plus pi is rational. It probably is. It would be really weird if it isn't. But it would be like the biggest shocker in mathematics since proving irrational numbers for the first time, would be if e plus pi was rational. But it could be. It hasn't been proven that it's not. And same with e times pi, but we do know that at least one of them is irrational. So we haven't proven both are, but we know at least one is. And I don't know if they actually use this method, but it reminds me of that at least. Now I have a combinatorial proof, which is showing that different expressions are basically counting the same thing in different ways. I imagine this could be reminiscent of almost using things like group theory or category theory or some of the more unifying backdrop fields of math, to show that two things map onto the same thing or contain the same properties, or what we can call isomorphic in other terms. And here they're saying like a bijection between two sets will show their sizes are equal. And for example, there are other expressions that maybe could equal the way a different way of describing factorial numbers. So if you could show that one of those expressions showed the amount of permutations of n objects, you would know that it also describes factorials because factorials describe that. So here we have a non-constructive proof. That establishes that an object exists, but we don't know how to find it or what exactly it is. And here is their example is a proof that exists that somewhere out there are two irrational numbers, a and b, so that a to the b is rational. And they don't use the fact that root 2 to root 2 is irrational. They just use the fact that root 2 is irrational. And this proof, if you didn't know that this is irrational, they note here it's not elementary. So if you prove this on its own, it could be harder to prove this case. They have a proof here that either that's a rational number, and we're done because that was what we were looking for. Irrational to rational is rational. Take this, or it's irrational. And so we can write a is that, and b is square root of 2. Then we raise a to b, which ends up breaking down to 2. So they've basically showed that either this one or this one are irrational. Are rational. Are either that's rational or that's rational. And here we can see that proof doesn't prove a particular case, but it does prove that they must exist. And sometimes there are bigger case examples of this, like any of these in math, where you can see like some mathematical... This is actually an interesting article. I read this a while ago. Mathematical object, because there's a lot of things it could be. And we assume maybe an object is a geometric thing, but not necessarily. And like a number is an object in math. So moving onward, statistical proof. And to anyone in our chatting, I will get to the chatting pretty soon after we go through this article and before the rest of it. Here we have statistical proofs. And these are often used in areas like cryptography, chaotic series, and these things they're describing. I don't know exactly what they're describing here, but statistical proofs sounds kind of similar to probabilistic proofs, but I actually don't know about those types quite as much, so maybe I'll study them more later. And here we have computer-assisted proofs. And those are a type we already mentioned. So after this, we are going to look at some other types of proofs. Like I said, we will probably move onward, at least for a bit, to some of the sillier types of false proof techniques that people may use or abuse to try and prove something. And then maybe if we have time in the stream, I also have a few articles that are specific proofs. Maybe we'll look through one or two specific proofs later. First, to look at our chat. Thank you all for joining me today. Love all of my combo lords. Somebody said they're new to my content. Hope I'm doing well. Yeah, I've had a complicated last few months, but I'm doing well at the moment. And in fact, it's a good time, I guess, to share randomly. I came up with a really cool math thing related to prime factorizations that, although it's simple enough that I'm sure someone or another has fiddled around with it briefly in the past, I could be the one who's fiddled around with it the most in history because I can't find anything about it online. I never like to commit to saying you discovered something because with simple concepts, you never know. But it's something I can't find in other info about that I found a really cool pattern within prime factorizations. And so that's going to be an episode or two from now. That's why I say you always got to save a main episode just in case lightning strikes. And this was a different type of lightning. So the next episode coming out probably this weekend of Combo Class will actually be, and that's on my main Combo Class channel, remember, not on this one, my favorite episodes, is actually one about a mathematical nature phenomena. That one's a little shorter, probably around 10 minutes, still be a fun one. And then after that, there'll be an episode about this new thing I discovered. And then there will be the finale of grade -2. Then a very short break just for a couple weeks, and then grade -3. So, somebody said proof by exhaustion low-key feels like mathematicians just becoming too tired to keep working on a problem. Although it sounds kind of like that at times, there are circumstances where the only current way of proving something is to prove that a massive data set holds. Sometimes data sets massive enough that you could not have a bajillion humans working on it to get there. One example would be if you wanted to prove that the 1/1,000,000th digit of pi was a certain digit in base 10. It shouldn't matter mathematically that much what that digit happens to be, but let's say you wanted to prove that just as an example. You couldn't, with any amount of humans on the planet, putting any amount of time in, calculate 1,000,000,000,000 digits of pi in any reasonable time frame. So you'd have to use a computer. So, we're going to have to collaborate with the computers in the future. I'm not a big computer lover. I like that they do things that help me. But at the same time, apart from what I need to use computers for, I'm not a big technology guy. I don't, go out and love buying any new technology that's not necessary to me. And so, still, I'll say, we're going to have to work with the computers. They're going to be here to stay for a bit, and we have to collaborate with them. Don't let them be your boss, but you can use their help in certain ways. And one example is that you're watching this stream. We wouldn't be able to do that without computer-like devices. And somebody notes proof assistants and verifiers make them look pretty surveyable. And as long as you trust the logic of certain programs, such as Lean was mentioned here, well, that is trusting a robot in a different way, in a more meta way. But, I would say that helps, but still the question remains, to what degree does that add to our trust of something? Does it take our trust all the way there, or what percent? Because scientifically, you always say that even things like gravity are not 100% proven. It's just like 99 point an absurd amount of 9% proven. And so, because it's just non-scientific to say certain things are 100% proven. And so I like to keep that logic in math a bit too, even though, we trust proofs, that if a proof's pretty complicated and there's only, handfuls of people on the planet who understand it, we do have to question how many nines we have after that 99, maybe. So, moving forward, actually, sorry, but I gotta go to the bathroom real quick, but I'll be back very shortly. And we're going to look at something extra fun then, which is going to be some of the strange, more joke types of proofs. And I will, for now, what will we put up? Let me leave this open just for folks' curiosity. I'll be back very shortly. But for now, just for the next 2 minutes or so, why don't you folks read through a few descriptions of really long proofs? And this is funny that proofs have gotten longer. Maybe because they have multiple authors more often, or maybe because other reasons, like maybe mathematics is a more appreciated field, so people are able to dedicate more time to it. I'm not sure why this is the case, but they say that back in 1900, 100 pages was really long for a proof, and now 500 pages is really long for a proof. Well, that was in 2000, so they don't even have a stat for right now. Anyway, these are some long proofs, and I'll be back shortly. Okay, folks, I'm back. Oh no, I was hovering the mouse over something that was blocking some of it. Sorry about hovering over this, but it's kind of interesting. You're like, why do they have... What's interesting, this is what I love about places like Wikipedia. You can get interested in a concept just from wondering, why do they have an article about this? Because you know they don't have an article about a polygon of 43,821 sides. They don't have an article about all the amounts of polygons up to that. Why do they have that? Well, it's based on really interesting things about geometric constructions and which shapes are constructible or not, which turns out to relate to all sorts of other things in math, including what are called Fermat primes, primes of a certain power of 2 form, a specific one. And so we'll have an episode about Fermat primes and constructible polygons at some point. Maybe we'll get even a little more geometric next grade, because grade -3, threes are reminiscent of not only triangles, which are in some ways the simplest 2D shape, and I guess they're contending with circle, depending how you define simple, for its simplest 2D shape. Technically a line, it exists in 2D, but it doesn't require 2D. Now, also, -3 is sort of reminiscent of 3D, so maybe we'll go into the -3rd dimension. Now, what we're going to look at next, before we maybe look at a few, specific proofs, is some sorts of funny examples of names for sorts of proof techniques that people use. And let me begin by saying that as a math channel, I encounter a lot of comments that say somebody has the comment saying, I've proven so-and-so thing. And you just know it's not. Some of these things that they're saying they're proving are like the Collatz conjecture, the Goldbach conjecture, the Riemann hypothesis, some of the biggest studied open questions in math. And so many people claim they've proven these things by now that it's practically known that you'd only trust somebody saying it if it's published in a scientific journal, especially because you would want to publish your results for that in a scientific journal, because it would be groundbreaking. You'd be famous if you proved any of these things. And a lot of these proofs, I've not looked over all of them, but I've looked over some, and some of them verge on really bad logic. They often verge on calls to random philosophical thoughts, such as, bring in some philosophical thought that you might relate to, and then saying that helps prove that this implies the Riemann hypothesis, or something that, is not much more a tangible thing you're trying to prove with a very subjective, surreal sort of philosophical concept. I've even seen somebody commented a playlist, maybe I'll have to go through on stream sometime, that they said, look at this playlist. I'm not sure if it was their videos or not, that they said, this contains proofs of this big open problem. I forget which one of those, but I think it was one of the ones I mentioned. And it's either those or like the twin prime conjecture, or one of the other really big studied open questions. And in this playlist, the videos kept verging into flat earth beliefs. It would start using either flat earth to try and prove math, or use math to try and prove flat earth. And it's like, whoa, I already didn't believe you've proven the Riemann hypothesis. You don't have to tell me now that since you've proven the Riemann hypothesis, the Earth's flat. So, some of the methods that people may use to falsely try and show they have proven something include this list of joke types of proofs. We have proof by obviousness. All you gotta say, nobody wants to be dumb. They don't want to miss something obvious. So you just gotta go, where? I'm trying to find where the cutoff for this is. All you gotta say is, it's so obvious. Yeah, anyone would get this. And then they just gotta get it or they're dumb. You have proof in general agreement. Everybody agrees that this statement is true. How could you not believe it? You have proof by imagination. Well, wouldn't it be really fanciful and nice and fun if this was true? Here's a cool scenario where it's true, that the scenario is so cool that how could it not be true? Proof by convenience. Oh man, it would be really hard if this thing wasn't true. We don't want it to be false. Let's just have it be true. Proof by necessity is sort of similar, but maybe in more dire times. Proof by plausibility. Oh, that sounds really good. It's got to be true. That sounds really accurate. Proof by intimidation. Now, proof by intimidation is actually one of the more commonly used terms as a net term to describe some of these ones. And because of that, there was actually a Wikipedia article about that one, proof by intimidation. So we'll come back to proof by intimidation. Now, proof by lack of sufficient time. Oh man, I gotta turn in my PhD thesis tomorrow, so it's true. Proof by postponement. This proof is so long that it's gonna be in the sequel. Proof by accident. This is maybe the only type that actually could be genuinely a proof. Oh shoot, what have we stumbled onto here? Proof by insignificance. Who really cares if it's true or false? I'm just gonna call it true. Proof by mumbo jumbo. Okay, this is another one that could be technically true, but it sort of just like scares the viewers away. It's hard for them to know if it's true or false because you're like, these are all the symbols that I expect you're using the same as me. Here's a joke one, proof by profanity, and oh boy, do I want to give some examples for fun, but I'll bite my tongue. Proof by definition. We define it to be true. It's one of our axioms now. We've added a new axiom. It's true. Proof by tautology. This is also another one that is actually could be a proof, but in a very trivial way. These are like, well, 2 equals 2. Proof by plagiarism. This is the bit I got least when I read through this earlier. I understood this one the least. First of all, they spelled plagiarism wrong. Second of all, as we see on page 289, how's that plagiarism if it's like on page 289 of their book? Are they meaning it's a book with multiple authors and it's on page 289? They butchered this joke, but moving onward. Proof by lost reference. Okay, there was this proof out there somewhere. I read it in a book once, trust me. Proof by calculus. They're joking that if it requires calculus, you'd skip it. Proof by terror. When intimidation fails. So when we go back to the proof by intimidation article later, remember that if proof by intimidation doesn't do... Oh my god, that's a massive mosquito. That's why I was itching. Oh god, you blood-sucking freak. I normally don't condone hurting any animals, of course, but mosquitoes are an exception. Now, when that sucker comes back, that sucker's dead. Now, normally when you call someone a sucker, it's not so literal as with a mosquito. Anyway, remember when we come back to proof by intimidation, that if that always doesn't work, you have a further resort. Proof by terror. Okay, now proof by lack of interest. I feel like we had that joke earlier, didn't we? Didn't they already put that joke in here? Yeah, that's the same as proof by insignificance. Come on, guys, that's the same joke. Okay. Proof by illegibility. We're running out of room here. It's like, I'm just gonna make it big. It doesn't let me scroll down on this page easily because it's like weird. It hits the bottom. Like I said, I'm not a tech guy. I don't know how to add stuff to the bottom. Now, proof by logic. Well, if it's on the problem sheet, it must be true. Some of the ones they have here could actually be a term, but, you know, they put a joke in that part. But some of these are, you know, purely things that seem like a joke even in the term, but I swear people put these in their proofs, or their proofs. Now, proof by majority rule, only to be used if general agreement is impossible. Proof by clever variable choice. So, X is going to be define X as the number where our hypothesis holds, and proof by tessellation. This proof is the same as the last. That is sort of a good gag if you literally were copying the proof, including the hypothesis, but then you'd kind of have two of the same proof. Proof by divine word. Now, we're not going to get into... Oh my god, there's that giant... Ugh. Oh my god, the mosquito... Okay, I got it. Look how big that mosquito was. I don't know if you can... Oh my god. This is like the... And it looks like a fly. But it was biting me. And it is a mosquito when you look at it up close. That's like... Oh my god. It's a fly-sized mosquito. Jesus. Okay. Hopefully you didn't bring any friends. Now... We're not going to get into religion, but yes, this is brought into some of the proofs in the comments I have seen people claim to have, that they use their proof by religion. Proof by stubbornness is, I don't care what you say. I think it's true. It doesn't matter if you need your proof. It's true. Proof by simplification. This proof reduced to the statement 1 + 1 = 2. There's another one that theoretically could be a valid technique. It might be tricky to get it down to that state, but maybe. Proof by hasty generalization. Well, it works for 17, so it works for all reals. Proof by... now, I'll note that with the problem I've been working on with prime factorizations that I noted a minute ago, that I stumbled onto something cool. I've been working on that the past week or so a bunch, and I'm not a computer programmer, so to test numbers, I test them by hand myself, using calculators and stuff, and writing it down in Word documents and notebooks. And I'm not, a master prover, so I'm trying to prove things about the pattern I found, and it's quite tricky and interesting to find how to prove certain things. Some of the things that seem obviously true, that I'm pretty sure of, I find a good proof for. And some of the things that seem pretty obviously true, but I'm not sure, I can't find a proof for, so I'm not sure if they're true or if I'm being tricked, So, proofs are a whole art. Now, here we have proof by deception. I like this gag. Proof by deception. Now everyone turn their backs. Yeah. So if you know some good sleight of hand, that always helps if you're presenting a proof at a math conference. If you mess anything up or if you have to divert the attention to a different part, well, cause everyone to look to the side for some magical reason and switch something on the whiteboard. Proof by supplication, they say, is, oh, please let it be true. Proof by poor analogy, they say, is, well, it's just like. Proof by avoidance is the limit of proof by postponement as it approaches infinity. I don't know if they put proof by postponement on. Oh, yeah, they did. Proof by postponement's up there, so that's good. Proof by avoidance is the limit of that proof as it approaches infinity. And then we have proof by design. Oh, yeah, this is actually a really common one you'll see people pull out. Proof by design is, well, I came up with a math system where this hypothesis I can prove. And the problem with that is you haven't proven that in your new system that things from our system still hold. And when you invent a new system with new rules, a lot of the simple rules break. Maybe A times B is not always B times A anymore. Maybe there's no longer certain rules we know about natural numbers, addition, or primes, or all that. So when you invent a new system, you sort of have to start from scratch and keep track of what are the things I've proven in my system. And a lot of people mish and mash it. And one example is people will say, I invented a variable that, like a new letter, for example, not a variable in terms of it changes, but one of like a constant represented by a letter, I guess I mean, that, although they treat it like a variable in ways, that equals 1 divided by 0. And the problem is that when you make up this new number, the way that division's normally defined, now you multiply and you're saying 0 times that is 1. And then if you say that what's 2 divided by 0, and they say, well, it's 2 times my constant. Well, now we're saying that 0 times that is that. And you start hitting these contradictions with how any number can be defined with all the rules we know about it, and you lose like everything. And so although you get the fun fact of we can now say 1 divided by 0 as a number, you lose all the other stuff. And so, not all the other stuff, but a lot of it. And so there are systems that try and allow it, but you have to treat them as different systems, and they don't assume they have the same things proven. So, you got to be careful with this one. Only make up a new rule if you're sure that it's already provable in the current system, or if you're willing to have your new system be the sort of wilderness that you know that you don't know much about what's proven in it yet or not. Now, proof by authority. Well, Don Knuth says it's true, so it's got to be. Shout out to Donald Knuth. What a great guy. I don't know if any of you know him, but he is one of the people who wrote some of the papers I first read about alternate bases. Now, proof by intuition. I have this gut feeling. They sort of ran out of steam at the end with these gags, but there's some funny ones on here. And now, there's actually one more set of gags we'll quickly go through before we move on. There's another page's set of gags of this. And this is actually a whole page of math gags on what's called Proof Wiki. And I saw, it's Proof Wiki has a article about proof methods, but it turns out that was buried in this thing of all these random mathematical jokes. But maybe we'll do all the random mathematical jokes another day. Today we are doing, joking and unjoking about proof methods. So here are some of the ones they mention here that weren't mentioned on the other are proof by triviality. And that one is sort of like the proof by tautology. But basically it's just saying, oh, one of the axioms is proven. And it's like, well, yeah, it's one of the axioms. Then you have proof by example. Oh my God, I hate mosquitoes. It's already developing this. It made 2 bumps. Oh my God. It's already developing this giant itchy bump where the mosquito bit me. I hate that guy. He's already dead and I still hate him. So, proof by example. Proof by example. 3 is larger than 2. Here are 3 apples. I took one away, now there's 2. Proof by exercise. That's one that a lot of textbook authors like to do when they don't want to include the proof in their book. The two, also, this one's sort of a joke, the proof by triviality, because although in this case it is actually trivial, it's sort of a joke that in a lot of math books, the author says something is trivial when it's kind of not. When it's like, it's only trivial if you are really well versed in like many fields and know all these assumptions about all those fields. And it's like, whoa, what do you mean it's trivial that this thing is a monoid? It's like, whoa, how's that trivial? So, certain ones, it can be kind of funny when they use the word trivial. Be careful if you use that word as an author because, it can put viewers off. I don't know why it's so popular in math. Like, calling something trivial sort of implies if you don't get it that you're dumb. Now, the other one that authors often use when they don't want to include the proof is, this is left as an exercise for the viewer. I guess they actually put both of those jokes in this one because they stuck a trivial in there. Then you have proof by a non-existent citation. For the proof of Fermat's last theorem, see Fermat's commentary on Arithmetica, which I assume doesn't exist. Proof by margin size. It's kind of interesting they did 2 Fermat gags. They did 3 Fermat gags. Are these all Fermat gags? Oh my God, they're all Fermat gags. Not all of them literally, but like Out of these five, 4 out of these 5, the joke is related to the mathematician Pierre de Fermat. Okay, this author really either loved or hated him. I don't know. They're jokes. So did they love Fermat or hate him? So this is a joke on Fermat, an actual note that Fermat left where he said he had proven this magnificent theorem that wasn't proven until many years later, more than 100 years later, by Andrew Wiles in not until the 1990s, and Fermat was in the 1700s, and he wrote in the margin of one of the books that was found after his death that he had proven this really great thing, that you can't have a to the n plus b to the n equals c to the n for integer solutions and variables that are larger than 2. And I mean non-zero integer solutions. So positive integer solutions for the base numbers and variables larger than 1 is the normal formulation. And I mean variables larger than 2. And the variables, yeah. The variables are the same larger than 2, 1. Anyway, I made an episode about that a while ago. But they keep doing these Fermat gags. Proof by authority. Fermat said it's true, they say. The proof by reduction to wrong problem. We reduce it to the Chinese remainder theorem. I assume that in this author's eyes it was reduced to the wrong problem because it wasn't a Fermat-based problem. Now, proof by generalization in the obvious way. To prove Fermat's last theorem, they say, we generalize his proof of the n equals 4 case in the obvious way. Yeah, the obvious, right. That is actually something that people sometimes, do accidentally, is like, oh, I proved it for this case, and so, yeah, it should hold for all the others, right? Proof by lack of counterexample. That's just when you only checked so many. And some other ones here that are sort of specific gags. So we're just going to kind of skim through these. And yeah. So, and this is a proof by a crank mathematician, and while this is a really purposefully badly written one on purpose to be a joke, some people do have shockingly bad spelling and grammar in what they say are the proofs of the Riemann hypothesis and such. I'm not one to criticize if somebody has bad spelling or grammar in a random post online or a comment or in their notebooks or whatever, but maybe formalize it if you're saying you've proven $1 million, literally $1 million worth problem. So moving onward, let's take a quick look at why Wikipedia has a whole article on proof by intimidation. Now, here they're noting some of the common ways it's used. They can see trivial is there. Okay, these two that I mentioned are on there. And other ones similar, if the author's trying to dodge it in a way, they'll say clearly, or it's self-evident that, or it's easily shown that, or it doesn't warrant a proof. And proof by intimidation, to me it also sounds sort of like when you appeal to emotion. There's a lot of, logical fallacies people can use, which a lot of them are appeals to certain things. Like an appeal to religion would be saying, if you believe this religion, then you have to believe the proof, or you're a bad believer of it. And a proof by appealing to authority would be saying, oh, the government says this, so we better believe it. And a proof of appealing to, what was I thinking? Emotion would be, when you tap into almost bullying someone into wanting to believe your proof by making them feel like they would have a bad emotion if they don't feel it, because you line up their emotions, or at least attempt to, with whether or not the proof's right or wrong. And if you are successful at that, for the worse, then you would successfully line up someone's emotions in a way where they're like, well, now I'll feel worse if I don't believe that, so I better believe it. And then they will accept a lot of these type of things. So proof by intimidation, just in terms of the name, sort of reminds me of that. But here's an example of when they say who it was coined by, they say it was originally about this guy. And man, this guy got roasted in this article. This whole article, proof by intimidation, was a technique used by this dude, they say. So they say when somebody interrupted his lecture by pointing out a glaring mistake he'd made, he became red in the face, raised his voice to a full shouting range. Sometimes he would ask the objector to leave the class. And they say that after his lectures, proof by intimidation was coined. During one of the lectures, the hearer was made to feel privy to some wondrous secret, one that often vanished by magic as he walked out of the classroom at the end of the period. How? That's a weird mix of things. Doesn't sound like a student would feel that. Maybe that was his attempt, or maybe he was really charming somehow, but it sounds like he's screaming, red in the face, and making people leave the classroom, so I don't know. I don't know if the students actually were feeling that. Anyway, those are some more joking ways that one may attempt to prove something. Taking a peek quickly back at their comments. Somebody says that they would, for example, trust Andrew Wiles' proof of the Fermat's last theorem more if it was formalized in something like Lean, which is something to check and formalize mathematical language. And while that would certainly help, his proof has been pretty checked at this point. So it's very complicated. It's not on even my level to check that, but there are mathematicians who have checked his proof, and he had to edit it even after it had been checked when it was released, and he edited it about a year later. It was published in 1993 and edited in 1994. And as far as I know, it hadn't required any edits from there till now. So it's pretty well studied. So that one's pretty trustworthy. But as a general point, that is true. And somebody asked, is it possible to make money in math without a formal education? Depends what you want to do in math. I make some money from math, and I don't have a specific, like, PhD in mathematics or anything like that. So, certainly it is possible. If you mean just from doing things like what we're studying here, like writing proofs, or, I mean, we're not writing them right now, but if you mean if you were to prove something interesting, I wouldn't count on just being able to prove things leading there. Now, if you want to make money off math, the best, most logical path, although that's not necessarily what I took, would be to become a teacher of some sort. Theoretically, if you market yourself very well and you are good at it, you could be a private teacher without requiring a formal education. You could have private students that you tutor. That is a way to make money off math. It will be harder to market yourself without a degree in that, but it's possible. I used to be a private music teacher, and I never had a music degree. I would just think I'm good at it, and I've studied it a lot. And so I did that by working at a music shop for a while and working my way up toward that within a system. And so it's possible, but if you are to want to make money off math, although this is not necessarily the path I followed myself, I went more into teaching than being sitting in 5 bajillion years of classes, because I personally learn better from reading books and stuff. I would recommend go to as much math classes as possible, but anything's possible. Now, somebody just left a nice comment, and I appreciate that. Thank you very much. And hello to the Hey as well. So thank you all for joining. And what I wanted to look at real quick before we wrap up was a few examples of some specific proofs, not necessarily going through all the details of them, but I mentioned that it was pretty difficult to prove that pi is irrational, and I wanted to show you some details on the ways you do prove that. And we are just going to look at Wikipedia, and I did pull this open for fun just to show. Sometimes you want to prove something funny, very simple, just to show proof techniques, or just test what you can do with different techniques. And so here's like an interesting one. What are different ways you can prove that 22/7 is larger than pi? And we're like, in the modern day, well, obviously just look at the decimals and then it's bigger. But how do you think they got those decimals? Well, at least at the beginning, the way that they got new decimals was narrowing ranges of it being larger than this fraction but smaller than this one. And so how can we prove, if you didn't know anything apart from, let's say, pi is bigger than 3. Let's say you don't even know that. Let's say you just know pi is the ratio of the circular things that it is. How can you prove that 22/7 is larger than it? And here we can prove that it's not a perfect representation of pi in simpler, but let's say we want to prove it's larger. Well, here's one proof. That one is very short, but we have to take an integral of a, sort of rough thing right there, but it's very short and nice. These are the details of actually evaluating that integral. And there are other ways. And here, down here, they show that this fraction exceeds pi. Now, more to, what I mentioned, pi being irrational. Well, what I mentioned in the episode about that was just this, that the general sense of the proof was that it was proven by this guy by showing that tangent of x has this infinite continued fraction. And you see this pattern, 1, 3, 5, 7, x, and then the rest are squareds. And it's cool when you get a continued fraction with a variable in it, and so this is true for so many things. It tells us tan 1 is this continued fraction where these are all 1s. Tan 2 is this continued fraction where that's 2 and these are all 4s. And so this guy proved that this was true, and then that if x is non-zero and rational, not tan of x, but x is non-zero and rational, then this whole thing ends up being irrational. So if x is non-zero and rational, tangent of x is irrational. Now you can show that tangent of pi over 4 equals 1, and 1 is rational. So this is sort of a proof by contraposition in a way. We saw that one earlier, that if 1's rational, then the opposite of that must be true. Because if that was true, it says it's irrational. So that must mean that x is not non-zero and rational, which means that pi over 4 is irrational, and so pi is irrational if pi over 4 is. And they say a simplification of the proof, because this is like the synopsis of the proof. The simplification is given here. This is actually what a simplification of that proof looks like. And that is why I didn't fit it into my last episode. There are other ways as well. And while we're not going to go deep into them, it's interesting to see what techniques they use. This one here uses the characterization of pi as the smallest positive zero whose half, so half of pi is the smallest positive number, is a zero of the cosine function. That's funny because this is like the sine or cosine function right there. And uses that to prove pi squared is irrational, and we end up getting to pi being irrational. And this is a simplification of that proof. Here's another way it's been gone, integrating things by parts. Here's another one that shows that pi, not pi over 2, is the smallest positive zero of the sine function, kind of similar to that other idea. Here's one that uses this calculus-y thing, including factorials. Here's one that was the simplification of Lambert's. And there we go. In the episode, I did show on screen for a moment a quick version of a proof that E is irrational, but what about pi for today? Because I did flash it on. Maybe E is actually simpler enough that maybe someday we'll do an episode where I actually do that proof in an episode. Maybe someday we'll do it for pi. Who knows? But here's one that I found that I haven't really double-checked this, but this seems to be, given, as I said, which assumptions of the proof do we consider we have to prove within the proof? Because there are certain things that we're like, well, we know this to be true. And, here's one, by Stirling's formula. So, do we prove that, or do we assume that that's already proven? So assuming that already proven stuff is already proven, and we're assuming those are separate here, this is the shortest proof I've seen that pi is irrational. So here they're going for each positive integer b and non-negative integer n. These may seem similar, positive and non-negative, but remember, this just means this one could include 0, that one can't. Define this. You gotta love these things. If you hadn't been led here by your mathematical studies over many years, you'd be like, how did they find this? Now, note that the integrand function of this is 0 at x equals 0 and x equals pi, but strictly positive elsewhere in this range, 0 to pi, that is being integrated. Integration is a calculus thing. Now, thus, it's greater than 0, this thing. Now, here we can write this whole way of reformulating it, which is less than 1 for large n, since by Stirling's formula, this thing increases faster than that power. And those are the variables there. So they've demonstrated that the denominator increases faster than the power will make it increase. Now, for any integer here, we've proven that this thing that they whipped up, for any b larger or equal to 1 and all sufficiently large n, sometimes you need to say this where it's not true for small values, but it ends up not being necessary to have the small values, that there's a point where after that point, all numbers will fill it. And here they're saying it's between 0 and 1. Then they prove all this stuff, and they prove all this stuff, and eventually they have proven that it must be an integer, but they had previously proven it was between 0 and 1. So an integer being larger than 0 but smaller than 1 is a contradiction, so now this ends up at that point having proven that pi is irrational. So I'll look through this more later on my own to see to what degree I can decode this. Pretty complicated equations we got here, but it's short for a proof of pi's irrationality. Now, that was all the pages I had pulled open here. Thank you to everyone who's joined me and left random comments and stuff. I guess I will wrap up pretty soon, and a reminder that if you want more proofs, make sure you've seen on my main combo class channel my last episode that shows ones like the square root of 2 and a logarithm and stuff, and some philosophical thoughts about it. My next episode will be out this weekend about this mathematical nature phenomena, and then the one after that will be this cool thing that I've been playing around with prime factors that I just stumbled into less than a week ago and have been hooked on testing different numbers and finding where the patterns go, and there were a few surprises. And like I said, this might be the last live stream for a little bit. Probably won't be too long, but that will only be because I want to get back into turning more of my ideas into bonus videos on this channel, as opposed to random live streams, which are less digestible for some folks. And so the next few things on this channel will probably be either shorts or random bonus videos that will be probably filmed by myself, maybe even on the same computer camera instead of my typical way, but will be more condensed into, one topic that I have a little plan for over a 10 or 15 minute video. Some of those will be little bits that didn't fit into main episodes this grade, and so this grade's a good time to throw them in as some bonus facts and stuff. Anyways, I'll tell you more about what's going on in my world in the finale, which is the 3 episodes from now, before we move on to grade -3. And over this next month or two, I have a lot of cool plans for what to do to wrap up this grade on these channels. And for now, I hope you all have been having a nice time watching. Hope you all have a nice night or day. And I'll see you next time in our combo realm. If you want to do some cool mathematical investigations of your own, try and think of some today's, homework or whatever, if you want, is think of a very simple mathematical statement you know to be true, and think of some ways you could prove it. Might be harder than you think. So, I will see you guys in the next